equation. You could do it as one equation, but the one equation would be Q is equal to the sum of the Q's of the individual steps. And then you'd have to do it. You have to figure it out. All right, that was chapter 15. Are there any questions in chapter 15? Chapter 15 dealt with pure solids, pure liquids, pure gases, except for the first part. The first part of chapter 15 we dealt with gas mixtures, like air. Air is what we call a solution. You know, solutions are homogeneous mixtures, and so air is a gaseous solution. But you know, we have different types of solutions. We have gaseous solutions like air. We have liquid solutions, which we're most familiar with. We have solid solutions, probably less familiar with. Solid solutions are things like alloys. And so we have gaseous solutions, homogeneous mixtures. We have liquid solutions, homogeneous and solid. Solid solution would be like brass or sterling silver or 18-karat gold. Those are all solid solutions, but they look pure. They aren't. They're mixtures. They look pure because the dispersed particles are very small. You can't really see them there. And you can tell that they aren't pure because, you know, pure substances have a fixed composition, whereas solutions can have variable composition. Air, you know, does air have a fixed composition? No, air has a variable composition depending on where you are. Sugar water is a homogeneous mixture. Does it have a fixed composition? No. It could be more concentrated or less. So this is a little bit about solutions. There's some more terms here. When we're dealing with solutions, there's the solute and the solvent. The solute's dissolved in the solvent. And so for air, it's a little tricky. What is the solvent? What's the solute? So what we do is we fall back. The solvent is in greater quantity. The solute is in lower quantities. And so in air, we could say that the oxygen is dissolved in the nitrogen, but it seems a little bit confusing. Whereas the oxygen would be the solute, nitrogen would be the solvent. It's a lot easier if we're doing sugar water. If we do sugar water, the solute is sugar, the solvent is water. A lot easier. This example. This is copper. This is copper 2 chloride. Can you tell what the copper is? Chloride? The gray, the copper, the chloride? The gray is the copper. The reason is because of this. Do you remember what happens to anions? Anions double in size from their parent. You know, so chlorine versus chloride. Chloride's twice as big. Chlorine. Cations shrink to about half the size. So sodium versus sodium ion. And so the general trend, when you look at I don't know if you saw this, but when you look at the chart, the ions, the general trend is all the anions are bigger than the cations, save for a few exceptions. And so, in general, anions are bigger than cations. So, the anion would be bigger. So, if we take a scoop of this and dissolve it in the water, then the solute is going to be this copper 2 chloride, and the solvent will be water. This will be our solution. The solution looks very homogeneous. It looks pure, but it's a mixture. It's a mixture of water and this. Okay, if we would look at it in detail, you can't see it looks homogeneous because these particles are so small. So we got the chloride ions, we got the copper 2 ions. Interesting thing happens with the chloride. Look at the orientation of the water.
we look at the orientation of the water, the hydrogens point to the chloride. Whereas when we look at the copper, what points to the copper? The oxygens. That's because the oxygens, the water is polar. The oxygens are negative end of water. So negative is attracted to positive. Whereas the hydrogens are the positive end, those can be attracted. And this attraction is actually pretty strong. This is what we call a hydration sphere, or hydration. This water encapsulating the ions. Hydration or solvation. Solvation is what we're using. The solvent is encapsulating the ions. You can see different ones. One here, another one here, here, here. That'll help stabilize it. Well, how much, if I took another scoop of this and put it in here, then what do you think would happen? It dissolve and the color would darken. Yeah. And what if I dump the whole thing in there? If I dump the whole thing in there, I could make what we call a concentrated solution. But is there a limit to how much will dissolve? Now, chlorides are all soluble except for silver, lead, and mercury, so this is soluble. But how soluble is it? Is it infinitely soluble? So I could just keep scooping it in there. No. There's going to be a limit to how much of that we can dissolve.
Sleep clinical care, formulated with unique
There it is. And so we could go to Wikipedia and take a look. A lot of this physical data is here. And we have something called solubility in water. You learn the solubility rules. The solubility rules is it soluble or not soluble? But what do you call soluble? What you call soluble is if you can dissolve more than 0.1 moles per liter. Which we certainly can do with copper, but we can't dissolve an infinite amount. In fact, there's a limit, and that limit itself is called solubility. So solubility is defined as the maximum amount of solute you can dissolve in a given amount of solvent. This is 70.6 grams dissolved in 100 milliliters of water. That's at 0 degrees C. If we increase the temperature to 25 degrees C, what happens to solubility? Does it stay the same? No, it actually goes up. At 100 degrees C, it becomes considerably more soluble. And so that makes sense. The higher the temperature, the more soluble. The higher the temperature, the more soluble because there's more kinetic energy. And so it can break apart the crystal a little easier. So these are aqueous solutions here. So there's a limit. The closer we get to this limit, the more concentrated it is. The further away from this limit, the more diluted it is. If we're right at the limit, let's say at room temperature, we're right at 75.7 grams per 100 milliliters, then we call that a saturated solution. We're right at the limit. And so these are all saturated solutions here, the maximum amount. Now, it doesn't have to be an aqueous solution. We could have something like methanol. If we look at the solubility of methanol, methanol would be the solvent. The copper 2 chloride would be the solute. So we take some crystals of copper chloride, like here, which has this lattice here, copper chloride. You can dissolve 68 grams of copper chloride in 100 milliliters of methanol, 15 degrees C. In ethanol, 53 grams. Methanol, ethanol, they're polar like water. Methanol, hydrogen bond like water. A little less soluble in ethanol. But it's soluble in acetone. What do they mean by that? That means this. That means there's some things that are infinitely soluble. An example of something that's infinitely soluble, I'm going to mention this before, is water. How much water can you dissolve in water? How much water will dissolve in water? An infinite amount. There's no limit, right? You can dissolve as much water in water as you want. Well, methanol is very water-like. So how much water or how much methanol can you dissolved in water, or vice versa, infinite amount. Same thing with ethanol. So this appears to be what we call infinitely soluble in acetone. But pretty soon, acetone stops being the solvent, and it switches. We end up probably with solid solution. But let's take a look. And so we have concentrated and dilute solutions. Concentrated, a lot of solute, dilute a little. But it's all relative, depends on what the solubility is. So this is a dilute solution of copper 2 nitrate. This is a concentrated solution of copper 2 nitrate. There's a whole bunch of other junk in here too. But you can tell by the color, light blue versus dark blue. It's more concentrated. As we get more and more concentrated, eventually we're going to hit the solubility, which is a saturated solution. But we still aren't there. These are 2 unsaturated solutions here. Actually, these are both the same solution. They just let the reaction go longer. This is a piece of copper wire twisted in silver nitrate. So a single replacement reaction. We precipitate out silver crystals. You can see the silver crystals here. As the silver crystals grow, they grow into these. Do you see these look like trees in a way? These are dendritic crystals. You have a tree-like pattern. These are all big crystals of silver. So the silver metal precipitates, the copper dissolves. The copper metal dissolves. So you see more copper too here. It's after several weeks. So solubility has 2 meanings. Qualitative, the solubility rules, will it dissolve, won't it dissolve? That's meaning, or definition 1. Definition 2 is the maximum amount. How much solute can dissolve in grams or whatever else. And so those are the 2 definitions. Actually 3 definitions of solubility. And so 1 was from the solubility rules. 2, the maximum amount. 3 is, we'll talk about in just a minute. If we have a saturated solution, we've hit that limit. We can't dissolve anymore. That's it. If we have an unsaturated solution, we're below that limit, the solubility limit. Okay, let me talk. The third way that soluble is defined is this. How soluble is water in water? How much is there a limit to how much water you can dissolve in water? No limit. When it's infinitely soluble, we call it miscible. Miscible means infinitely soluble. However, your book is calling miscible soluble. I call it miscible infinitely soluble. That is soluble without limit. If we look at this Wikipedia entry, take a look at this Wikipedia entry here. It says methanol, 68 grams per 100 milliliters. Ethanol, 53 grams per 100 milliliters. And then it says soluble in acetone. What are they talking about soluble in acetone? They must be saying miscible in acetone or something. Infinitely soluble. Acetone. I don't know if that's right. Probably a typo, but you got to worry about this because sometimes they don't catch the typos. Sometimes there might be mistakes. But there are a lot of people reviewing these Wikipedia entries. You can be reliable. So miscible, infinitely soluble, immiscible, insoluble. And so we have a very simple rule for molecular compounds. you know, the solubility rules for ionic compounds is a bit of a pain because you got to memorize it. In group 1 in ammonium, salts are salt soluble, a whole bunch of them. But the solubility rules for molecular compounds are so simple. So for example, octane and carbon tetrachloride are miscible in one another. They're completely soluble in one another. And so they'll dissolve in all proportions. So you can have all octane, a little bit of carbon tetrachloride, or vice versa, or 50-50. This is about a 50-50 mix. In a 50-50 mix, it's hard to tell what's a solvent, what's a solute. Well, it switches, so it doesn't really matter. One time it could be the octane's the solvent, but once the carbon tetrachloride exceeds that, then carbon tetrachloride will be the solvent. So the roles will be reversed. But they're miscible. They're miscible in one another because they really like each other. The reason they really like each other is because non-polar molecules, carbon tetrachloride is non-polar, and octane is non-polar. Octane is a hydrocarbon, 8-chain carbon. Both of these are non-polar, and they like each other because of the intermolecular force. You know, non-polar species have what type of intermolecular force? Attractive force. Non-polar species have what type of intermolecular force? Well, non-polar means they don't have a permanent dipole. If they don't have a permanent dipole, then they must have a temporary induced. This temporary or instantaneous induced dipole is called, well, it's called the instantaneous induced dipole attraction. That's the intermolecular force, but that's too long, so it's shortened. Instantaneous induced, that is temporary dipole, induced dipole is shortened to we don't call it because it's a mouthful to call it that, so instead we call it temporary dipoles are called London forces. And so they like each other because they both like, you know, both have London forces. You know, there's other names. In addition to London force, you could call it dispersion. So London forces are, you know, these temporary dipole forces. Dispersion forces are these temporary dipole forces. And one final name would be London dispersion. So London dispersion, and London force is all the same. They're the temporary dipoles. So temporary dipoles are set up and they like each other because they both temporary dipole. And so what we say is that octane and carbon tetrachloride are miscible in one another, infinitely soluble, or soluble in one another. Whereas, how about oil or gasoline? Gasoline and water, do they mix? No, gasoline and water do not mix, they're immiscible. That's because gasoline, like octane, likes to London dispersion or London dispersion or temporary dipole. Whereas water has a permanent dipole. Water has a very, very big permanent dipole called hydrogen bonding. So water has hydrogen bonding interactions. And so the rule for solubility for molecular compounds is very simple. Like dissolves like. So temporary dipoles like temporary dipoles, permanent dipoles like permanent dipoles. So these don't like, there's energetics, but we aren't going to get into the energetics. If I try to mix, what would happen if I tried to mix carbon tetrachloride with water? If I tried to mix carbon tetrachloride with water, would they be miscible or immiscible? Immiscible. The carbon tetrachloride would not dissolve in water. Carbon tetrachloride is heavier than octane, so what happens is the carbon tetrachloride sinks to the bottom rather than floats on the top. So in order to determine solubility, we just need to know, is it polar or non-polar? Polar likes polar, non-polar likes non-polar. Non-polar and polar don't like each other.
So that's to sum up this slide. Like dissolved like is the net result of this slide. That's the first part. This slide is 2 parts. The second part of this slide is let's look at something very polar. We're going to look at sodium chloride. You know, sodium chloride is extremely polar because sodium chloride has ionic bonds. Extremely polar. And so we're going to look at the when sodium chloride is placed in water. It's not a reaction; it's a physical process. It's dissolution, it's dissolving. What happens when sodium chloride is dissolved in water? Well, what happens is the negative ions on the surface, the sodium chloride, the chloride ions on the surface are going to be attracted to the positive parts of the water. In other words, the positive parts of the water are attracted to the negative ions. The negative parts of the water are attracted to the positive ions. So we could sum that up here. Here's sodium chloride, surface. In other words, a water molecule bumps in here and pulls the ion off. It's got to bump in here with some force to break it off, and then once it's broken off, it can encapsulate it. Encapsulate it so it can't go back. It encapsulates it like this. We call this a hydration sphere. And so water is getting, you know, the different energies of water. So some water molecules will have enough energy to break it, some won't. But if it does get broken off, we'll have this hydrated chloride. The same thing happens with the sodium ions, hydrated sodium. And we can see the red points to the positive, the white here points to the negative. In other words, the oxygens are attracted to the sodium, and the hydrogens are attracted to the sodium. Okay, this is going to stabilize this. That's the solution. So that's what they're saying in the first part here. They're saying once the ions are broken off, they get encapsulated by the water molecules, forming hydrated ions. That helps prevent them from going back. But they can still go back and stick. So we call this a reversible process. The reversible process is, yeah, those sodium ions are now hydrated. That's what the Na plus AQ, hydrated sodium ions. But those hydrated sodium ions, that sodium might break free, that is, break free from this hydration sphere and then stick to the surface. And so the reverse process is crystallization. So what could happen is this hydrated ion can come over here and crash into the crystal, and then this sodium ion gets stuck there. And then crystallizes out of solution. Both processes occur, but both processes occur in pretty much depends on how much, you know, of the solid and how much of the ions we have, hydrated ions we have. That's why we call it reversible, but it's not always reversible. So for example here, this is not reversible. What's going to happen is this. We got a lot of solid there, and this is just, let's say this is just pure water. What's going to happen is the crystals are going to dissolve. As the crystals dissolve, we're going to build up a concentration of hydrated ions. So here we have a low concentration. It's pretty dilute. But as long as we build up some ions here, then the reverse process can occur. That is, the ions can hit the surface and stick. The ions hit the surface and stick, that's crystallization. And so here we see the dissolving rate or dissolution rate and the crystallization rate given by the length of the arrows. As this continues to dissolve, more and more ions get put into solution. The higher the concentration of ions here, the greater the crystallization rate. And eventually what's going to happen is we're going to hit a point where the number of ions that dissolve equals the number of ions that crystallize. And so these are equal and opposite. And if they're equal and opposite, we hit a state of equilibrium. That is, there's no more change. And so once we hit the state of equilibrium, no more of this dissolves, and we call this solution saturated. It can't dissolve anymore. We hit that saturation limit. That saturation limit is where the dissolution rate, the dissolving rate, is equal to the crystallization rate.
Now, this is called equilibrium, but it's also called a dynamic equilibrium. It's called a dynamic equilibrium because can you stop dissolving? And can you stop crystallizing? You can't stop those, so those continue to occur. You're just going in circles. Even though you're going in circles, the crystals are going to change. The crystals are constantly dissolving and reforming. And so you're going to see things change, but when you weigh the amounts, nothing changes with the amounts. Dynamic equilibrium. We have to saturate it to get the dynamic equilibrium as well. If it's unsaturated, we aren't going to get that dynamic equilibrium. There's one more word here that's supersaturated. Supersaturation occurs when the crystallization is not so easy. We get supersaturation. Some things are easy to crystallize. Like sodium chloride is not so hard to crystallize. Sodium chloride is not so hard to crystallize. All we need to crystallize sodium chloride is that a sodium hits the greens. So this gray hits the greens, we're going to get crystallization. Or this green hits the grays, we're going to get crystallization because it should stick. Okay? But some things are hard to crystallize. Like sodium chloride is not that hard. Something that would be hard to crystallize would be sodium acetate. Why is sodium acetate so much harder to crystallize than sodium chloride? The reason why sodium acetate is so much harder to crystallize is because of the shape of the acetate ion. If we look at acetate ion, it looks like this. It has a complex shape to it. I mean, look at the first carbon. The first carbon is tetrahedral or square planar or trigonal pyramidal. This first carbon would not be called trigonal pyramidal because it would be trigonal pyramidal if you ignored this. Then yes, trigonal pyramidal. Or if you ignored this atom, trigonal pyramidal. But we can't ignore those, so we look at the electron geometry. The electron geometry is tetrahedral. And then we look at the atom geometry. The atom geometry is the same. So this first carbon is tetrahedral. The second carbon is trigonal planar. And so this has a complex shape. Compare this to chloride. You know, this is a -1 ion. Chloride's a -1 ion. What's the shape of chloride? The chloride ion is just a ball. It's a sphere. That's it. And so it doesn't have a complex shape. It has a very simple shape. It's just spherical. Well, when we form a crystal, you know, crystals are very well ordered. And so think about acetate. Acetate has to be perfectly lined up in the crystal. If the acetate's off a little bit, it's not going to crystallize because a crystal, you have to have a well-ordered pattern, and this pattern has to repeat. So each acetate has to be perfectly lined up in the crystal lattice. Is that easy to do? No, the probability of having the acetate line up perfectly is much, much lower than the probability of having a chloride lined up perfectly. And so what this means is this. It's hard to crystallize this because the acetates have a complicated shape to them. And so if you're trying to grow a crystal, you have to put everything together in the right position. So you start off with a sodium, that's easy, and then you put an acetate. The acetate has to be perfect. Then a sodium, and then another acetate, and the next acetate has to be perfectly aligned. If it isn't, you aren't going to get a crystal. And since it's hard to do, we call that nucleation. Nucleation is trying to grow a little baby crystal. It's hard to nucleate sodium acetate because everything has to be perfectly lined up. And so what can happen is this. You take some sodium acetate,
then we're going to make some saturated solutions. So at about 25 degrees C, that's really soluble. Sodium acetate's really soluble. Yeah. At about 25 degrees C, we're around 120 grams of sodium acetate for saturated. Then we're going to heat it up to close to boiling. If we heat it up close to boiling, then we can add another 40 grams in there. 40 grams. So we're at about 160 grams of sodium acetate. And then we'll cool it back down. If we cool it back down to here, then the solubility is 120 grams. So we have 40 grams of excess sodium acetate dissolved. Now what should happen to that excess 40 grams? The excess 40 grams should precipitate or crystallize out of solution. But is it easy to nucleate sodium acetate crystals? No, not easy. It's not easy. And so what that means is, it means that sodium acetate nucleation is sluggish. And if it's sluggish, what can happen is it doesn't nucleate. And so ignore this in the center here. But okay, so we had a hot saturated sodium acetate solution cooled back down to room temperature. Now we have 40 grams of excess sodium acetate per 100 milliliters. This is more than 100 milliliters. This is probably about 300 milliliters, 400 milliliters. 300 milliliters will be 120 grams of excess sodium acetate dissolved in there. It's a lot, isn't it? If this is 400 milliliters, that'd be 160 grams of excess sodium acetate. And so if the crystallization is sluggish, what we can do to help crystallization is we can take a little crystal here. This little crystal is called a seed crystal. And a seed crystal helps it out because if a seed crystal is dropped in there, that forms a template in which the other ions can attach to it, rather than starting from scratch. If you start from scratch, it's much harder. So what they did was they dropped a seed crystal in here, and that really helps crystal formation and growth. And so this is what we see. We see an excess of whatever, anywhere between 120 and 160 grams of excess sodium acetate precipitate out. It's probably easier to see in terms of video animations or live. Do this live, it's not hard. So let's take a look at this.
Okay, just really quick, I'm going to have one tiny seed crystal. I'm not sure if you can see it.
There's one tiny little crystal to form the template.
And we will see it go from a supersaturated state to a saturated state in just a few seconds. Isn't that cool? So we see that the sodium and acetate ions recognize the crystalline structure.
So over 100 grams of excess crystals. Excess solute there. Let's take a look at some of that. Oh, it's about to tip it over? Or? That little bit of liquid is saturated now.
Super saturated, saturated.
It's sodium acetate. Actually, this is interesting. They put the seed crystal in the center, so let's see what it looks like with the seed crystal in the center of it rather than on the surface.
In chemistry, we have available to us a fairly
actually, not this one.
diverse
Alright, this one's hitting the surface. There's one where they put it in the center so you can see it grow like in our figure in the book. That's saturated. Super saturated solution there. Who was that? Alright, this one is this one's a little different. This is putting the sea crystal on the table here.
Good luck. I thought it was Oh no. Come on, buddy, come on. Oh no, crystallizing now.
Alright, that's hopefully this is better power.
Look at it go.
The sea crystal there. Watch that.
Tower of sodium acetate coming out of a supersaturated solution. All over. I'm done.
No, I want to stand.
Are you sick?
There we go.
Me too.
There's the mashed reservoir hour there. Or leave it there.
Brandon, I think you're gonna win the award for the tallest sodium acetate tower.
Class award?
Is it hot?
Let's not touch it.
I was gonna ask you, is this an example of a stalagmite or a stalactite?
No. Can you touch it with your hands?
Okay, but anyway, that's the super saturated. Alright, so that's what happens with solids. Solids, what you do is you can heat them up and get those to dissolve more. That's what I was looking for.
So as you heat it up, the solubility increases. So as you cool it down, the solubility decreases and we should see precipitation. So a lot of these precipitate rapidly, like ammonium chloride. Ammonium's tetrahedral, so it's spherical, chloride's spherical. It's easy to crystallize. And so ammonium chloride hot, and it's cooled down, the excess solute crystallizes out easily. So it's harder to form a supersaturated solution of ammonium chloride because crystals are easy to nucleate. You need things that are harder to nucleate. That happens for most solids here. You know, it depends if it's hard or easy to nucleate, whether you form supersaturated or just form saturated like that. But there are some substances, when you heat them up, the solubility actually decreases, like lithium sulfate, and sodium chloride to some extent. And so, as these get hotter, they become less soluble. There are reasons for that in terms of energetics, but you just need to know the general trend. The general trend is solids, solubility increases with increasing temperature, more kinetic energy.
What about gases? Do gas solubilities increase with increasing temperature? And the answer is no. When we look at gases, the solubility actually decreases with increasing temperature.
for most gases. The reason it has to do with kinetic energy. I mean, if you have a gas that's dissolved in water, if you start increasing the temperature, you're going to knock the gas particles out of the water back into the gas phase. And so gas solubility decrease with temperature. One way to increase the gas solubility is to increase the gas pressure above this. So we can increase the gas pressure here, like this. That's going to just force more gas molecules into the liquid phase. So the concentration of the gas is directly proportional to the gas pressure. And so you could
See supersaturated solutions. In fact, you can buy supersaturated solutions easily, and that is like sparkling water. If we look at sparkling water is just saturated with what? Sparkling water is saturated with CO2. And so when you go buy sparkling water, it's completely saturated with CO2. Do you know what the pressure of the gas here is? Is it under high pressure, sparkling water, or just under normal pressure? It's under high. If you shake this up, it'll be under high pressure, but let's say it's just been standing for a long time. It's not shaken up. When you open the cap, is there a pressure release, or is it pretty much the same? Well, it depends. But basically, the pressure is very close, if not 1 atmosphere of CO2. And so the 1 atmosphere of CO2 is going to force CO2 molecules in, and CO2 molecules are going to be forced out. What happens though is if you open the cap, that CO2 is going to be replaced with air. And so if we open the cap and we let air inside, like this, we'll have air here. But do you know what the pressure of CO2 in air is? The pressure of CO2 in air, this is the partial pressure, is 0.0003 atmosphere. So we go from 1 atmosphere to 0.0003 atmospheres. That means we have way too much CO2 dissolved in here. Not enough that can sustain it. There's very little being forced in, and the same being actually a lot coming out. But the problem is the CO2 is hard to nucleate. And so we need a seed crystal. But a seed crystal of CO2 is not easy. So we can use other things as seeds. One other thing we could use as seeds would be Mentos. You know, the candy Mentos. And you've probably seen this. Right? So let's just take a look at using alternative seed crystals here. We'll just finish with this. We're out of time, so stop here.